What if everything we know about the universe is both perfectly right and still fundamentally incomplete? That is exactly what physicists mean when they say a phrase that sounds like science fiction. Physics is broken. But this isn't about collapse or failure. It's about something far more unsettling. It means our two most successful theories of reality refuse to fully agree with each other, even though both of them work almost flawlessly in their own domains. First, there is a dramatic misunderstanding that needs to be cleared away. When people hear that physics is broken, they imagine Einstein being wrong, relativity collapsing, and modern science falling apart. That version is simply false. Einstein's general relativity remains one of the most precisely tested theories ever created. It is not in crisis. It is not failing. In fact, it continues to pass every test we throw at it with astonishing accuracy. Every GPS satellite orbiting Earth must correct for time dilation predicted by relativity, or your navigation would drift within minutes. Observations from the Event Horizon Telescope match Einstein's predictions for black holes almost perfectly, capturing the shadow of a supermassive object exactly as relativity describes. Even the detection of gravitational waves by LIGO and Virgo followed waveforms that Einstein wrote down a century ago, matching reality with extraordinary precision. And the equivalence principle, the idea that all objects fall at the same rate regardless of their mass or composition, has been tested to extreme accuracy down to 1 part in 100 trillion. Nothing in these results suggests Einstein was wrong. But that is only half the story. The deeper meaning of physics is broken is not that Einstein failed. It is that Einstein's theory, despite being correct, does not fit together with another equally successful framework, quantum mechanics. On its own, quantum theory is just as powerful. It describes atoms, particles, light, and all the microscopic building blocks of reality with unmatched precision. It explains semiconductors, lasers, chemistry, and essentially all modern technology. It is not an approximation. It is not temporary. It works. And yet, these two pillars of physics describe reality in completely incompatible ways. General relativity treats space and time as a smooth, continuous geometric fabric that bends under mass and energy. Quantum mechanics, on the other hand, describes the universe as probabilistic, uncertain, and fundamentally discrete in its behavior. In quantum theory, nothing has a definite value until it is measured. In relativity, everything is smooth and precisely defined. When physicists try to combine these two frameworks into a single theory of quantum gravity, the mathematics begins to fail. The equations produce infinities that cannot be removed using standard methods. The same techniques that successfully fix quantum electrodynamics or quantum chromodynamics simply do not work for gravity. Instead of canceling out, the infinities multiply. Predictive power collapses, and this is where modern research begins to push into unknown territory. Around the world, including in advanced programs in China, scientists are testing where these two theories begin to show subtle cracks, not by breaking Einstein, but by pushing his equations to their absolute limits. Experiments using the Fast Radio Telescope, atomic clocks in space, and ultra-precise torsion balances are probing the boundary where relativity and quantum physics should begin to interact. So far, something surprising is happening. Einstein keeps surviving every test. No clear violations appear. But instead of solving the problem, this actually deepens it, because every confirmation narrows the space where a deeper theory could hide. And that leads us to a strange conclusion. Physics is not broken because it fails, but because it works too well in two different, incompatible ways that cannot both be the final story of reality. Nowhere is this tension more visible than in the experiments currently being carried out at the edge of modern precision science. At the center of this mystery are a series of experiments designed not to overthrow Einstein, but to find the exact place where his theory might stop being complete. One of the most important tools in this search is the Fast Radio Telescope in China, the largest single-dish radio telescope in the world. It observes pulsars, which are rapidly spinning neutron stars that emit incredibly regular pulses of radiation. These objects act like cosmic clocks, ticking across the universe with extreme precision. Scientists use them to test one of the deepest principles in physics, Lorentz invariance, which says that the laws of physics are the same for all observers moving at constant speed. Many theories that attempt to merge gravity with quantum mechanics suggest that at extremely small scales, space-time might not be smooth at all. Instead, it could be granular, almost like a quantum foam. If that were true, light of different energies might travel at slightly different speeds. The idea sounds small, but the consequences would be enormous. A tiny difference in speed, over billions of years of travel from distant galaxies, would accumulate into a measurable delay in arrival times. So FAST carefully analyzes signals from pulsars, looking for any mismatch between high energy and low energy photons. The result so far is simple but powerful. No deviation has been found. Light behaves exactly as relativity predicts, even across cosmic distances. This does not break Einstein, it strengthens him, but it also eliminates entire classes of proposed quantum gravity theories that predicted such deviations. The more precisely we test, the more constrained the possible new physics becomes. A similar story appears in another experiment: atomic clocks operating in microgravity aboard China's space station. These clocks use ultra-cold atoms, such as rubidium 87 and strontium 87, cooled almost to absolute zero. At this temperature, quantum behavior becomes extremely stable and measurable. Researchers compare how different atomic species respond to gravity. The question is subtle. If gravity affects quantum systems differently depending on their internal structure, then two atomic clocks should slowly drift apart over time. But once again, the result is negative. No difference appears. The equivalence principle survives even in the quantum regime tested so far. Meanwhile, another experiment focuses on something more mysterious: the gravitational constant, G. Unlike other constants in physics, G is surprisingly imprecise. Different experiments measuring it using torsion balances produce slightly different results that do not fully agree within expected error margins. Most scientists believe this is due to tiny experimental disturbances, vibrations, or thermal effects. But the inconsistency refuses to disappear completely. This raises a deeper question. What if this mismatch is not just noise? What if gravity itself behaves in a way we do not fully understand yet? Still, none of these experiments show clear violations of Einstein's theory. Instead, they produce null results. And in physics, a null result is not meaningless. It is a boundary marker. It tells us where new theories are not allowed to exist. Each negative result shrinks the space where quantum gravity might hide. This is where the situation becomes intellectually uncomfortable. Because the absence of evidence is not ignorance, it is precision. And precision is slowly cornering every possible alternative explanation. So instead of finding cracks in relativity, science is finding something even stranger. The universe seems to obey Einstein with increasing stubbornness, even as we know Einstein cannot be the final answer. The tension becomes even clearer when we zoom out and look at what these two great theories are actually describing. General relativity is a theory of gravity and space-time. It explains how mass and energy curve the very fabric of the universe, shaping the motion of planets, light, and even time itself. Its predictions are not abstract, they are visible everywhere. Black holes, gravitational waves, cosmic expansion, and gravitational lensing are all direct consequences of its equations. Quantum mechanics, on the other hand, governs the microscopic world. It describes particles like electrons, photons, quarks, and the strange probabilistic rules they follow. It explains atomic structure, chemical reactions, lasers, semiconductors, and all modern electronics. Without it, none of our technology would exist. Both theories are confirmed with extreme precision. Both are essential, and yet they describe reality using fundamentally different languages. Relativity assumes space-time is smooth and continuous, like a curved surface. Quantum mechanics assumes uncertainty is built into the foundation of nature. In quantum theory, particles do not have definite properties until measured. In relativity, everything has a well-defined geometric structure at every point. When physicists try to quantize gravity to treat space-time itself as a quantum field, the equations begin to break down. The usual mathematical tools that work for other forces fail. In quantum electrodynamics, infinities can be controlled through renormalization. The same is true for the strong and weak nuclear forces. But gravity refuses to behave. The infinities multiply uncontrollably, requiring an infinite number of corrections. A theory with infinite free parameters loses predictive power, which makes it physically meaningless. This is the central technical obstacle that has driven decades of research into quantum gravity. Theoretical frameworks like string theory, loop quantum gravity, asymptotic safety, and causal dynamical triangulation all attempt to solve this problem in different ways. But none has yet produced a complete, experimentally confirmed theory. That is why modern experiments are so important. They are not just testing Einstein, they are narrowing the possibilities for what could replace him. Large-scale observatories and precision instruments are now probing the smallest possible deviations from known physics. FAST continues to analyze pulsars across vast cosmic distances. Space-based atomic clocks compare quantum systems under different gravitational conditions. Torsion balances refine measurements of G. Gravitational wave detectors like LIGO listen for subtle distortions in space-time. Cosmological surveys map the structure of the universe in increasing detail. Each experiment produces the same type of result. No clear violation of known physics, but collectively, they tell a deeper story. The universe behaves exactly as expected under current theories, but only up to the limits we can test. This creates a strange scientific paradox. We are not finding errors, yet we are certain the picture is incomplete. It is like reading a perfectly consistent map that suddenly becomes unreliable beyond the edges of explored territory. And those edges are exactly where the next part of physics must emerge. To understand why this situation is so significant, we need to look at how theoretical physics is trying to move beyond Einstein. One of the most prominent approaches is string theory. It proposes that the fundamental building blocks of reality are not point-like particles but tiny vibrating strings. Different vibration patterns correspond to different particles: electrons, quarks, photons, and even the hypothetical graviton, which would carry gravity in a quantum framework. String theory has an elegant advantage. It naturally includes gravity without the mathematical infinities that plague other approaches. But it introduces a major complication. It requires extra spatial dimensions, typically 10 or 11 in total. These extra dimensions must be compactified into extremely complex geometric shapes, leading to an enormous number of possible universes. This creates what is often called the landscape problem. Instead of predicting a single unique universe, string theory allows an almost unimaginable number of possible solutions, each with different physical laws. The challenge is no longer building the theory, but explaining why our universe has the specific properties we observe. Another major approach is loop quantum gravity. Instead of adding extra dimensions, it tries to quantize space-time directly. In this framework, space is not continuous but made of discrete units, forming a kind of quantum network. However, this discreteness introduces a potential problem. It may slightly violate Lorentz invariance, meaning the speed of light could depend on energy. This is where experiments like fast and gamma-ray observations become crucial. If high-energy photons traveled at slightly different speeds than low-energy ones, we would see distortions in signals from distant cosmic events like gamma-ray bursts. But once again, observations show no such effect. Light behaves exactly as relativity predicts. These results do not kill loop quantum gravity, but they strongly constrain its simplest versions. The theory must be refined or modified to remain consistent with observation. Then there is an even more intriguing idea proposed by Roger Penrose. He suggested that gravity itself might be responsible for the collapse of quantum superpositions. In standard quantum mechanics, particles can exist in multiple states at once until measured. This is called superposition. But Penrose proposed that when a system becomes massive enough, its associated space-time geometry also becomes a superposition, and this state may be unstable. If true, gravity would play a direct role in the transition from quantum possibilities to classical reality. This idea shifts the focus away from high-energy particle physics and toward precision experiments involving increasingly large quantum systems. Modern interferometry experiments are now testing this boundary. Scientists can place atoms into superposition states and maintain coherence long enough to measure gravitational effects with extreme sensitivity. Instead of looking for high-energy collisions, they are looking for tiny phase shifts in quantum states. China's research programs in this area are expanding rapidly, focusing on ultra-sensitive quantum sensors that could test whether quantum systems respond to gravity exactly as classical systems do. And once again, the guiding principle is not brute force energy, but extreme precision. The future of fundamental physics may depend less on giant accelerators and more on extraordinarily delicate measurements. This shift toward precision reveals something profound about the direction of modern physics. Instead of building ever larger machines, scientists are building ever more sensitive instruments. Atomic clocks, quantum interferometers, torsion balances, and pulsar timing systems are becoming the primary tools for exploring the deepest questions about reality. These experiments all share a common pattern. They confirm Einstein again and again, but in doing so, they tighten the constraints on any possible new theory. Every null result removes a possible path forward for quantum gravity. Every increase in precision pushes new physics further away from what we can currently observe. This is why the phrase "physics is broken" carries such a specific meaning. It does not mean the theory has failed. It means the two most successful frameworks in science, general relativity and quantum mechanics, cannot both be the final description of reality. They each work perfectly in their own domains, but they do not merge into a single unified picture. For decades, string theory dominated attempts at unification. Its idea that particles are vibrating strings naturally includes gravity and avoids many mathematical inconsistencies. But its reliance on extra dimensions and its vast landscape of possible solutions has made experimental verification extremely difficult. Loop quantum gravity offers a different path, suggesting space-time itself is fundamentally discrete. But experimental tests of Lorentz invariance, including pulsar timing and gamma-ray observations, place strong limits on many of its predictions. Other frameworks, such as asymptotic safety or emergent gravity, continue to develop, but none has yet achieved a complete, testable, and widely accepted formulation. Meanwhile, observational physics continues to advance. Instruments like fast gravitational wave detectors, space-based atomic clocks, and cosmological surveys are steadily improving our understanding of the universe. They are measuring pulsars, black holes, dark energy, early galaxies, and fundamental constants with unprecedented precision. Interestingly, even cosmology is showing small tensions. Measurements of the universe's expansion rate, the so-called Hubble tension, do not fully agree between different methods. The nature of dark energy remains uncertain. Early galaxy observations sometimes appear earlier or more developed than expected. Even the gravitational constant G continues to show small inconsistencies across experiments. Individually, each of these may have conventional explanations. Together, they form a pattern that hints at something deeper. Our current model of the universe might be extremely accurate, but not complete. And this brings us to the most important realization. Physics is not broken in the sense of being wrong or useless. It is broken in the sense of being split into two perfect but incompatible halves. General relativity works, quantum mechanics works, but they do not yet work together. And somewhere at the edge of precision experiments, where measurements become more sensitive than ever before, the first real hint of unification may eventually appear. Not through dramatic collapse, but through a tiny, persistent deviation that refuses to go away. The work to repair this divide is already underway, and every experiment brings us closer to the moment where nature finally reveals what lies beyond Einstein. If you want more deep breakdowns like this, subscribe to the channel, stay curious, and keep following the edge of modern physics, because the next discovery might already be hiding inside the smallest measurement we have ever made.